Assalamu alaikum everyone. So in this lecture we will learn about boost converter. So the boost converter is also known as step up DC-DC converter. So if you compare with your buck converter and look at the circuit, then you can see that in buck converter the switch was placed in here, whereas you had your inductor placed at in this location. So whenever your switch was switching, so the input voltage came at the output for certain time, and for certain time when the switch was off, there was basically the switch was off, so the input voltage didn't come at the output side, so the output average voltage was lower than your input voltage, and that is what was the principle for buck operation. However, in boost converter we are using the inductor together with the input voltage. So for certain time this voltage in the inductor and the voltage from the input voltage will add and will show up in the output, and for certain time it will not. So if we look at the operation here, so when the switch is connected to this node, that means it is connected like this in the second figure. So our VL or the inductor voltage is basically V in minus V out, and at that time our inductor voltage plus the input voltage, so the voltage across the capacitor or the load is actually the input voltage plus the voltage across the inductor. That means at that particular time your V output will be higher than your V input, and in the second step when the switch is connected to this node, at that time basically you are charging your inductor. So for certain time you are charging your inductor, and for certain time the output voltage becomes the input voltage plus the inductor voltage. Now for the time when the inductor is basically charging up, at that time the output voltage will be maintained by this capacitor. So this is the boost converter in a very simplified way. Okay, so now if we look at the equations and if we derive the relationship between the output voltage and the input voltage, then we can use the Volt-Seck equation, and if we integrate the voltage across the inductor for the whole time period, then we know that the integration is equals to 0, and we have two steps. In one stage from 0 to t on, so this is step number 1. From 0 to t on, our inductor voltage is basically V in. At that time the inductor is charging up, or the energy is storing in that in the inductor during this phase. So our integration is limit from 0 to t on. And in the second stage, when basically the input voltage and the inductor is connected to the output, at that time our inductor voltage or VL is basically V in minus V out. Okay, and that limit is from t on to t. So if we do the integration, then we come up with something like this equation. So we have V in multiplied by t on plus V in minus V out multiplied by t minus t on, which is equals to 0. And after some simple algebraic manipulation, we end up with V out divided by V in, which is equals to t divided by t minus t on. And after further simplification, we end up with V out divided by V in is equals to 1 over 1 minus D. Now, as this duty cycle value or the D value varies from 0 to 1, our output voltage will also vary accordingly. For example, when the duty cycle value approaches to 0, or when the duty cycle is very small, at that time this D value is very small, so the denominator term is equals to 1, or it's approximately equals to 1, and at that time our V output is equals to V in. However, when this duty cycle value increases and when it approaches to 1 or closer to 1, at that time our denominator value becomes smaller. As a result, the output voltage becomes higher and higher, and as it approaches 0, V out will approach infinity. Now, of course, this is theoretically possible. In actual circuit, it's not going to be infinity, but it's going to be higher. And as it can be seen that in boost operation, for different D values, V out varies between V in to very high value. Okay, so now how this circuit is implemented, how these switches are implemented. So the switches are basically replaced with a set of a transistor, or it can be a FET as well, and a diode. So we will give the gate pulse here at the gate of the MOSFET, or at the base of the transistor. So depending on this on and off cycle of this switch, we will see how it operates. So when we give a gate pulse here, that means at that time this switch is on. So basically during that time the voltage at this point is lower than your output voltage, and the diode is reversed biased. As a result, this is open circuit, and we will have a current flow through the inductor, and the output voltage here will be fed from the capacitor. And when the gate pulse is off, at that time basically we are opening this switch, so we have one way for the current to flow, and also the voltage here is positive or higher compared to our output voltage, so the current will flow in this direction, and the diode is forward biased. So this is exactly the same way it operates if you correlate the circuit here. Okay, so if we look at the wave shapes of the inductor current, for example, to get that, we can look at the wave shape of the inductor voltage. So the inductor voltage during the time when this switch is on, that means the inductor voltage VL is basically the input voltage. So VL is the input voltage. So at that time, so if I write it here, so if you look at it, so this is the time when our switch is on, and this is the time when the switch is off. This is the time again when our switch is on, and during the time when the switch is on, our inductor voltage, or VL, is equals to V in. So this is equals to V in. Okay, so this value is equals to V in. And when the time when this switch is off, at that time VL is equals to V in minus V out. So VL is V in minus V out. V out is higher, so here something like this. So if we now we know that L di by dt is equals to VL, so this di is equals to 1 over L V dt, and if we integrate it, that means if we integrate a constant part, then we will have a slope here. So the current will be like a slope, and the slope of this IL, or the current value, is V in divided by L. So it comes from this equation, L di by dt is equals to VL. So if we do the integration, then you can see that it will be VL divided by L. So VL in this particular case is V in. So the slope of the current is V in divided by L. Whereas for the second part, our slope is minus V in minus V naught, or in other way it's V out minus V in divided by L. So this is the slope of your falling edge of the inductor current, which you basically get by integrating the VL, or the voltage across the inductor. Now if this is the current that is flowing through the inductor VL, then some part of it will go through the will go through the diode, and some part of it will go through the transistor or the switch. So during the time when this switch is on, at that time the inductor current, this amount of current will actually flow. So the inductor current in the rising edge will actually flow also through the transistor here, and the diode current at that time will be 0. Whereas when this switch is off, that means during the off time, this switch will be off, so there will be no current flowing through the switch, whereas the current flowing through the diode will be the same as the inductor current. Okay, and like this. So if we see, then we can notice that there is a DC component in the inductor current, which we normally denote as IL, I capital L. That means this represents the DC component. Now this I capital L is the same as the input current. Now if you correlate with your buck converter, then the inductor was placed on the right hand side, and at that time the inductor current, or the IL, was actually the DC component of the inductor current was the same as the load current. Now for boost converter, this IL is actually the same as the input current. So this IL is basically the same as the input current. Now if we look at the diode current, so this is the current that is flowing through the diode, and of course here the dotted line is the IL, and this diode current, the DC component of this IL, it will according to the duty cycle of this on and off duration, the output current will basically depend on this diode current. So the average of here is the output current which is flowing through the load. Okay, so to calculate it, we are calculating the area of it, which is T off. So the off duration multiplied by IL. So the IL here is this value. So our I naught is basically T off divided by T multiplied by IL. This is the average output current. Okay, so here it's shown that the output current, I output, is this, and if we manipulate this portion, divide it by I in, here if you divide everything by I in, if you divide I out divided by I in, and you also divide the right hand side by I in, then as I said before, this I in, or the input current, is the same as the DC inductor current, which is IL or the DC component in the inductor current. So you can basically cancel these two together. So you get I out divided by I in is equals to T off divided by T, which is actually 1 minus D. So your output current is 1 minus D multiplied by I in. So if you look at the operation from a current perspective, so as your duty cycle D will vary from 0 to 1, so your output current will basically vary from so there will be a step down operation in your output current. Now the efficiency of the system is the output divided by the input, and the output power is basically I out square multiplied by R load. Now this R load is often calculated if you know the output power. If you know the voltage, you can calculate. If you know the output voltage, you can calculate the R load. Otherwise, in some cases, you may be given the value of R load directly. So this is your output power, I naught square R load, and then your input power is the same as the output power plus the losses. Now these losses in the circuit comes from all the non-idealities, For example, from this inductor. So when the inductor is wound, it's basically a long wire or a long metal wire that is wounded and it forms the inductor. That means it has there is a physical length of the wire, and there is a certain thickness of this wire which contributes to the stray resistances. The stray resistances comes from rho L by A, or the resistance in that straight piece of wire that is wounded. So from that part of the wire you have a certain stray resistance. This value is typically much lower than the inductance value. However, this contributes to the losses in the system. It is also valid for the diode. So the diode has during the time when the diode is on, there is a voltage drop across the diode. There is a constant voltage drop across the diode, which causes a power dissipation across the diode when the diode is on. And where for the switch or the transistor, there are basically two kinds of losses. One is the switching loss. So whenever this switch is transitioning from an on state to an off state, or from an off state to an on state, there is, so for example during this time there is a switching loss due to this on and off, and also there is a conduction loss. So whenever the switch is on, so during the time when the switch is conducting the current, so at that time again there is a finite voltage drop across the switch, and there is a current flow. And now this current flow and the voltage drop causes a loss in the switch, which is known as the conduction loss in the transistor. Also the capacitor here is not ideal, so this capacitor will also cause some losses. Furthermore, as this circuit is physically built, so it must have some physical connection. It will consist of wires, it will consist of some metallic conductors, which will again contribute to some resistances that are distributed along these lines, so which will also contribute to the losses in the system. Now we have to keep it in mind at this point that all these losses are basically due to the resistance, or due to the resistive nature, and it will increase the temperature of the circuit. Now as I said in the previous classes, in the class of buck converter, the challenging part here is that these stray resistances not only reduces the efficiency of the system, but it also increases the temperature of your circuit. So as an engineer, one of your main tasks will be how effectively or how efficiently you can cool down your circuit, or you can reduce the temperature of your circuit, because reducing the temperature is essential, otherwise you will basically damage your circuit components, because all these physical components, the characteristics of it depends heavily on the temperature. Okay, so if we look, if we only consider, in this case we have only considered the RL, or the stray resistance in the inductor. So now the losses are not only coming from the stray resistances, the losses will come from other diode resistances, or the diode, the forward voltage drop from the diode, from the on and off switching losses, and the conduction losses of the transistors from the capacitor. So all these losses, but for simplicity here we are only considering the stray resistance of the inductor, which is denoted as RL here. Okay, so this is the amount of your input power. So the input power is the sum of the output power plus the loss. And if we do the manipulation here, then we can see, if we divide it, divided by I square R load, then it will be 1 divided by 1 plus IL square divided by I naught whole square multiplied by RL divided by R load. Now this RL divided by R load, we are defining it as alpha, and then we have IL square, IL divided by I naught whole square, which is basically, if we look at the output and the input current, this IL is basically the input current, so it is 1 divided by 1 over D whole square. And if we do the manipulation, it looks like this equation. So our efficiency can be represented by this equation, whereas our input and output voltage is related to 1 divided by 1 minus D. So if we vary the duty cycle D from 0.1 to 1, then we will have different efficiencies, and we will have different output voltage as well, or the ratio of the output and input voltage. If we plot it, you can do this simple calculation considering a real life example. So if we have a certain input and output voltage, if you know a certain D from that input and output voltage, and if you know this ratio of the RL divided by load resistance, then you can calculate the alpha value. And if we put this D value like this, the duty cycle values, then you can calculate what's the value of the efficiency and what's the value of the gain, what is the value of the voltage gain. And if you plot it, if you plot the gain and the efficiency, then it looks somewhat like this, that your efficiency after as the D is increased, and if you look at the equation, as the D is increased, so this value becomes higher than this part, and when the D value is smaller, then basically it's closer to 1. But as the D value is getting closer to 1, that means this part is getting higher than this part, and your efficiency will drop as it approaches 1. Whereas our gain, it will have a behavior something like this. So after a certain point, because as the D value here is approaches to 1, and at that time you will have a sharp fall in the gain. So when you design it, your design criteria is that you look for an efficiency which is typically in the range of 90% or more than 90%, and you also need to maintain certain D so that your output divided by V input is not compromised. Now if we look at the choice of the inductor, so this choice of the inductor lies on the inductor current, and for continuous inductor current, that means for the time when the inductor current is not going to 0, So we have to derive what should be the value of the inductor value so that our inductor current does not go to 0. Now if we look at our inductor wave shapes, if we look at it here, this inductor current, then we can see that depending on the value of the L, so the higher the value of the L, the lower the slope, or the lower the value of the L, the higher the slope. So there will be a value of L for which your slope will basically touch this x-axis, and as a result at that time you will have a discontinuous current operation. Now our objective is to find what will be the value of the L so that we can find a continuous inductor current operation, and we will calculate it from the IL max and IL mean value. So the IL max is IL, or the DC part of the inductor current, plus from this this delta IL. Now this delta IL value is basically half of the slope during the time when it is on. So the on time is d multiplied by t, and your slope is V in divided by L. Okay, so your V in divided by L is the slope. So your IL mean is IL, or the inductor DC part, minus half of V in divided by L multiplied by dt. Now at the boundary operations, this IL mean will be 0. So it will be 0 equals to IL minus V in divided by L multiplied by dt. Now we know that for boost converter, this IL, or the DC component of the inductor current, is basically the input current, or the current that is coming from the source I in. So if you replace IL with I in, and then you replace this I in with output current, so you replace with output current divided by 1 minus t, okay, and then this part again comes from this is V in. Okay, so I did a mistake, so here should be half, we should have come half here. Okay, so there should be also half here. There should be a half here and a half here. Okay, so minus half of V in divided by L mean. So this L is basically the L mean multiplied by dt, and if you do further manipulation for the V in, if you replace V in with V out, and you get I out here. So, and if you do simple manipulations, then you end up with half of R multiplied by D into 1 minus D divided by F. Okay, I think this is 1 minus D square, because this T is 1 over F, this 1 minus D is 1 minus D, so it should be 1 minus D square, and then your V out divided by I naught is basically the R, and D comes from here. Yes, so this is 1 minus D square. So this is your L mean, or the minimum inductor equation. Now if we look at the value of the capacitor, or what should be the value of your C, then you can basically look at the wave shapes. So we have our inductor current like this, IL, and as I said, this diode current, or the current through the diode, will only flow when this transistor is off. That means during the off time, the diode current is basically the same as the inductor current, and then this diode current will be split into two parts. One will go through the load, and as we are saying that the output current, or this I naught, is basically linked with the input current and the duty cycle, so it's 1 minus D multiplied by our I in is equals to I naught. So I naught is somewhere lies here, so the rest will flow to the capacitor. So the capacitor current will look like this. So it will be a fixed negative value which will be equal to minus I naught. The value here is negative of I naught, and then during the on time it will rise again, and then it will follow the wave shape like this. Now to calculate the value of C, what we are doing here, we are following the same approach that we did during the buck converter. So the dq, or the delta q, or the amount of charge that is being stored for this amount of time when the current is negative, at that time if we find the area, then you know the current and the time. So if you multiply these two, you get the charge, so which is equals to I naught multiplied by dt. So I naught multiplied by dt is equals to dq, which can also be written as C dV. So your C dV is basically V out divided by R. So basically I naught is V out divided by R multiplied by dt, and from here you get this dV by V naught. This is the ripple, the percentage ripple. So dV by d naught is equals to d divided by CRF. You are replacing your t with the frequency f here. Okay. So depending on your design need, so normally when you are asked to design a circuit, you are also asked to design it for a certain for a certain ripple factor. So if it is said, or if it is mentioned that okay, make a circuit for 1% ripple or 0.1% less than 0.1% ripple, then you should choose your C value accordingly, because here if you look at this equation, so your duty cycle D is basically coming from the voltage ratio. So this duty cycle D is set from whatever is your input and output ratio. So depending on whatever output voltage you want, your duty cycle will be defined from that. So you cannot play with this duty cycle anymore in order to change the ripple and your frequency. So you have two important, so your R, or the load, is also again fixed in some cases. Maybe in some applications it's variable, but in some cases it will be fixed. So you cannot probably play with R, or you have a certain range of R that you know that this resistance will vary from this range to that range. So you cannot play with this R, and then you have two things that you can play with. One is C and the other is F. And normally your switching frequency, you try to adopt this switching frequency at a higher value. The reason is that the higher the value of a switching frequency, the magnetic circuit, or the inductor here is a magnetic circuit, the dimension of this magnetic circuit will be much smaller, or the higher you increase in the frequency, the smaller the F is. But there is a limit of this switching frequency, how high you can go, because the higher the switching frequency here, you increase the switching losses in this transistor. So there is a limit beyond which you cannot increase your F. You normally try to increase your F because increasing the frequency will reduce the size of your circuit, but there is a limit after which if you increase your F, your losses will increase more and more. So above which you are not interested to increase your F anymore. So you have only one parameter that to play with, basically with capacitor C, to have a certain ripple factor at your output. Okay. And that C value should be so the minimum C value, whatever you are calculating, your actual C values should be higher than that minimum value, because the higher the C, the lower the ripple, or in our real world, the lower the ripple is, the better it is. So and these capacitor values normally they don't come in all these integer values. So you will have certain specific values, maybe 220 microfarad, and then the next step is 330 microfarad. So if for example, if you calculate it and if you find that your capacitor value is 250 microfarad, so the next available option is probably 330 microfarad. So you have to go to the next available option. Okay, then we will see one numerical problem here. So in the numerical problem, it says that a boost converter is operating at fixed frequency of 100 kilohertz with a constant duty cycle and is fed by a 100 volt low ripple DC voltage source and delivers 150 output voltage at nominal power output of 300 watt. So our output power is 300 watt, our input voltage is 100 volt, our output voltage is 150 volt, and our switching frequency is 100 kilohertz. The inductor has a peak-to-peak current that is 100% of the average current. So first we have to know what is the average current here, and the 100% of the inductor average current is going to be the 100% of it is going to be the peak-to-peak value. So the output voltage ripple in this example is negligible. Okay, so it says draw the circuit diagram and label the important voltage and current. So here is your circuit diagram. So this is our input voltage 100 volt, the output voltage is 150 volt, and this is the current flowing through the load IR, or you can represent it as I out as well. This is the current IC, this is the diode current flowing through the diode ID, and the transistor current IT. This is the inductor current IL, and this duty cycle is defined from this input and output values. So you know the relationship between output and the input value, and from there you calculate the D value, and this TS is basically 1 over F, and as the F value is 100 kilohertz, so our time period is 10 microsecond. Okay, so in the next question it says that sketch the inductor voltage and the current waveform. What is the value of the L? So the inductor voltage waveform is like this. During the on time, or the time when it is on, the inductor voltage is basically the same as the input voltage, so it should be equals to 100 volts. Whereas during the time when this switch is off, at that time the inductor voltage is basically V in minus V naught, and V naught here is higher, so it will be minus 50 volt. So you see, and if you do the integration here, then you get the inductor wave shape, current wave shape like this. Now as is said, the IL value, or the DC component of the inductor current, is basically the input current, or the current that is coming out from the input. Now if you assume that the efficiency of the system is 100%, of course, which is not in real life, is not 100%, but is close to 100%. So if you assume that the input power is the same as the output power, then your input current is 300 watt divided by 100 volt, which is equals to 3 amp. So this is the DC component of your inductor current, and as it said that the ripple of the inductor current is basically 100% of this value. So delta I is 3 amp, that means the peak to peak value is 3 amp. So IL max is 3 amp plus 1.5 amp, and IL mean is 3 amp minus 1.5 amp. You can also calculate it from the slope. So once you know the time, once you know the slope, so you can use your intermediate geometry formulas to calculate the intersecting point of this at a certain point. So if you know the slope, if you know when what is the value of this intersection here with the DC component, then you will be able to calculate IL max or IL mean as well. Okay, so the next task is says that what is the value of the L. So to calculate the value of the L, you know that this V is equals to L di dt. So from here you can calculate the value of the L. So in this particular example, you were asked to calculate the value of the L. So the ripple was given as delta I is equal to 3 amp. In other numerical problems, maybe that will not be given, maybe your inductor value is given, and from there you may be asked to calculate what is the value of the IL max and IL min. Okay. So the third question says that they determine the average and the RMS diode current. So this is the current that is flowing through the diode, which is actually this current. So the current when the current slope is falling, this is the diode current, and during the on time the diode current is 0. So the wave shape is something like this. So the maximum of the diode current is 4.5 amp, the minimum is 1.5 amp, and as our duty cycle is 33%, so it will start at 3.3 microsecond, and then the time period is 10 microseconds. So this is our diode current wave shape, and the average value of this diode current is, you can calculate it from the output current as well. So the average diode current is basically 300 watt, that is the output power, divided by the output voltage, which is equals to 2 amp. You can also calculate it from the input input current and the duty cycle. Okay, and for the RMS calculation, you know this equation, you know these points in Cartesian plane, so you know the equation, so you can calculate what is the RMS value of this diode current. I am not doing it here. So now if we try to simulate this circuit in Simulink, then basically I built again a very simple circuit. I will give it to you. You can play with this circuit and then see how much you can understand from it. Okay, so this circuit is again drawn keeping in again drawn for the mathematical examples that we have just solved. So our input voltage is 100 volt, and our output voltage should be 150 volt. So our duty cycle it's here, the pulse generator is 33%, or the duty cycle is basically 0.33. Okay, and the period is 1 over frequency, which is 100 kilohertz here, and then we have our diode here, we have our inductor L here, and we have our capacitor here. As in the example, the capacitor value is not mentioned, so I have chosen as 500 microfarad as the capacitor value. Now if I run it, if I run the circuit, I need to wait a little bit for the results to come. Because I am doing this simulation for a bit longer time than normally what I did before. This is because there is a transient phase at the beginning which disappears after some time. So if you look at here, then you can see that there is a transient phase which basically disappears after certain time. So if we look at our steady state time, so if we look at our steady state time, okay, so our input current is basically this one. This is the current that is coming out from the input, or this is the inductor current, is the same, and it is this part of the current. Okay, and the diode current is basically the time when the switch is off. So during the off time, you can see this is the diode current, and when it is on, the diode current is 0. And our load current which is a fixed value of 2 amp here. So this is our load current, and if you subtract load current from the inductor current, then you get if you subtract the load current from the diode current, then you get the capacitor current IC. The IC looks like this, and if you integrate this part of your IC from that equation you get you get the value of the capacitor. And if you look at your voltage here, so your voltage, the output voltage is 150 volt, so you are having a stepping up operation, or the voltage is increasing. Okay, so now if you again look at this circuit, then you will probably see not so significant ripple. There is certain output ripple here as well. Okay, so this is the amount of voltage ripple, which is not so high. So this is the output voltage, and the ripple lies in 159.17 to 159.3 approximately. Now this value will obviously increase if you reduce this value of your capacitor C. So if you run it, and then you will be able to see that for a reduced value of C, your output ripple will basically go high. You can also play with the switching frequency, but in that case the other parameters will also change. But this is also an option to do that, which is not often done using changing the switching frequency, but it can be done. The easier option is to change the value of the C for a certain ripple voltage. And here is your inductance value L. So you can increase your inductance value or decrease your inductance value. If you reduce your inductance value, there will be a certain value of L for which you will have discontinuous current operation. So this is again a very very quick and simple simulation, which will probably give some insight of the topic that you are learning. Okay, so with this I would like to conclude today's lecture. So we will discuss it again in the discussion class. So if you have any question, we will see it in the class. Thank you very much. Have a nice day.